Here to start chapter 7, we're going to look at confidence intervals. More specifically here in the first section, confidence intervals for the mean. The mean, and I'm going to add on to here that our population standard deviation is known. That comes into play as we move further into the chapter. Gives us some more information to deal with. So what we're doing here with confidence intervals is we're going to take some information, some statistical analysis, and construct an interval, a range of values that we can be a certain confident or a certain percentage confident that our population value falls between there. So for example, let's say I want to find the average AC or estimate the average ACT score for all the entire student body at Waukee High School. Okay, so rather than try and find every student at Waukee who's taken the ACT test and find the average from those, which would be our population mean, the population of Waukee High School, I could take a sample. So maybe I take everybody in the statistics class who's taken the ACT, have their ACT score, find their mean. That would be the sample mean. I would then use that along with our statistical analysis, our normal distribution curve, and those types of things to estimate where our population mean for the entire value of Waukee High School might fall. So the first point to make here, the point estimate is the phrase that's used. Point estimate, the best point estimate is the sample mean. So the best way to estimate the population mean is to use the sample mean. Best way to estimate the population mean, let's backtrack on that. Best way to estimate the population mean is to use the sample mean. So our best point estimate of the population mean is the sample mean. We have three common confidence intervals. 99%, the z-score we use for 99% is 2.58. The next confidence interval is 95%. That z-score is 1.96. And the third one is 90%. That z-score is 1.65. So those are some common ones that are used. Those aren't all inclusive. Kind of a side note there, what that is doing on our normal distribution curve is, let's say we have a 90% interval. That means 90% of the scores are going to fall between here or out here, and what we call the tails of the curve is a total of 10% or 5% on each side. So alpha is that area in the tails of the curve, or 10%. Hence down here, you see in our formula, we'll get to this in just a second, is alpha divided by 2. So we take our alpha and divide it by 2 to find our z-score. So anyway, alpha is the area in the tails of the curve. Our confidence interval is this area in between 90, 95, or 99%. The actual formula itself to calculate a confidence interval is pretty well spelled out here. X bar is our sample mean. Our z-score comes from table E. Table E is what we used here in chapter 6. Our sigma here, Greek letter, is our population standard deviation, and the square root of n is our sample size. So X bar is the sample mean. Z-score comes from table E, based on our table up here. Those common ones are 1.65, 1.96, 2.58. And then our sigma is our population standard deviation, and n is our sample size. So calculating the confidence interval should be pretty straightforward once we can identify that information. So looking at our first example here, the president of the large university wishes to estimate the average age of students presently enrolled. From past studies, the standard deviation is known to be 2 years. So I'm going to underline that. Past studies, our standard deviation, that tells us our standard deviation is sigma, our population value, and that allows us to use table E. Knowing that is the one criteria that tells us what table to use for our z-scores. A sample of 50 students is selected and the mean is found to be 23.2. Find the 95% confidence interval of the population mean. So once again, our interval is our sample mean, which is 23.2. There's our X bar right there, sample mean, minus our z-score for 95% is 1.96. Our standard deviation of the population is 2, and our sample size is 50. And on the other side, we have the same part of the formula, except we add the 1.96 times 2 over the square root of 50. And if we go to alpha, or to our calculation here, I get 22.65 here and 23.75 here. Typically, we'd like to go one more place value than the given data here. So notice our sample mean was the nearest tenth, so we'll go to the nearest hundredth down here with these calculations. Now, just for a minute here, I'm going to backtrack and show us how we use the curve to come up with a z-score for 95%. So as I mentioned, 95% goes on either side, and this middle part here shaded is our 95%, which means outside of that I have a total of 5% or 2.5% on each side. So from here I would go to our table and look up inside the table the number closest to 0.025. So I'm going to go up here. 0.025 is right here. It actually comes out exact this time, so you can 0.0 to 0.025. If we work our way back, you see negative 1.96. Now, for our purposes, we don't use the negative value, but you can see that we use 1.96 on each side. Okay, so there's the easiest way to illustrate the idea of finding our z-score. Again, that's written as z sub alpha over 2 because alpha here is actually 5%. We divide it in half to get the area in each tail of the curve, or 0.025. Oh, we'll move on to a couple more examples of our confidence intervals. Sample of 48 has a sample mean of 416. Sample mean is X bar. Population standard deviation of 15. So again, for today's purposes, we'll just identify that, and I'm going to note that that is the one indicator that tells us to use table E or a z-score, knowing the population standard deviation. Population standard deviation is 15. Find the 95% interval for the population mean. So 416 minus our z-score for 95% again is 1.96. Our standard deviation is 15, and our sample size is 48. Setting that up around our population mean, 416 plus 1.96 times 15 over the square root of 48. And if we make that calculation, I have 411.76 to 420.24. So backtrack a little bit, I didn't really cover this with the first question. What this information is telling us right here is we can be 95% sure, in other words, with a 5% chance of mistake, that our population mean is going to be between these two numbers based on the information we have up here with our sample size, our standard deviation, our sample mean. So in our previous example, or the president of the large university, we could go to the president and say, hey, we're 95% sure that our average age falls between 22.65 and 23.75 years. Back here, finishing this one off, we have 411.76 to 420.24. We'll go one more time here. Find the 99% confidence interval for a population mean of a sample of 45 as a sample mean of 83. There's our X bar. Population standard deviation of 3.5. Population standard deviation is sigma. And once again, that allows us to use table E or our z-score in our calculation. So our sample mean is 83 minus our z-score for 99% this time is 2.58. Our standard deviation is 3.5, and our sample size is 45. Constructing an interval for the mean, population mean. So 83 plus 2.58, 3.5 divided by the square root of 45. And that calculation would get us 81.65 to 84.35. So once again, we're 99% sure that our information is going to fall between, our population mean is going to fall between these two numbers based on our work with statistics and our normal distribution curve. All right, one more time here. A survey of 30 adults found the average or the mean age of a person's primary vehicle is 5.6. So our survey of 30, that gives us a sample mean of 5.6 years. Standard deviation of the population, and population standard deviation tells us that we have sigma, and that uses table E or our z-score. Find the 99% interval of the population mean. 5.6 minus our z-score for 99% is 2.58. Our standard deviation is 0.8, and our sample size is 30. And we'll construct the same part of that interval on the other side, but we'll add that. Z-score once again for 99% is 2.58. 0.8 over the square root of 30. And if we make that calculation, we have 5.22 to about 5.98. We're 99% sure the average age of somebody's primary vehicle falls between 5.22 and 5.98. Okay, so there's a look at our confidence intervals. We have a second formula in this section. This one's for the minimum sample size. So notice each of these previous problems said something about finding the confidence interval. Find the 99% interval. Find the 99% confidence interval. Up here, find the 95% confidence interval. These next problems, we're going to find the minimum sample sizes needed, or how large a sample. So we're looking down at this example, how large a sample is necessary. But back up here, here's our formula. N is our sample size. Z is our z-score. That's the 1.65, the 1.96, or the 2.58. Sigma, our population standard deviation. New variable here, E is our maximum error of estimate, how accurate we want to be. So E again is our maximum error of estimate. Big thing here is regardless of the decimal, it will almost always be a decimal, always round up to the next whole number. So if I have 6.01, I still round up to 7. I have 6.99, I round up to 7. So we always round up the decimal regardless of whether it's a small decimal or a large decimal. Always round up to the next whole number, again because a minimum sample size, so a sample size is going to be a whole number. Example, college president asks the staff teacher to estimate the average age of students at their college. How large a sample is necessary? So again, how large, we're not constructing an interval, finding out how many, or we're finding N. The staff teacher would like to be 99% confident, so 99% confident gives us a z-score of 2.58. Accurate within 1 year. 1 year will be our maximum error of estimate, how accurate we want to be. And from previous studies, the standard deviation is known to be 3 years. There's our sigma. So I'm going to we got the formula right up here above in front of us, so I don't need to rewrite it. But our z-score is 2.58. Our standard deviation is 3 years. And our maximum error of estimate is 1. And if anybody forgets to do something, they typically forget to square this, so I am going to just basically underline that. We're going to square 2.58 times 3. In this case, I really don't need to divide by 1, but I'll mention it. We divide by 1, and if we do that, we get 59.9076. We round that decimal up, so the minimum sample size that we need is 60. We have to have at least 60 people surveyed in order to construct this interval that the president wants. One more time here. Find the minimum sample size needed to estimate a population mean if a population standard deviation is 24, sigma. Confidence interval desired is 90%, that's 1.65, or our z-score. And our maximum error of estimate is 5, that's our E. Pointing out back here at the very beginning, find the minimum sample size, N. We're not finding a confidence interval, we're finding a minimum sample size, or N. Our z-score for 90% is 1.65. Our standard deviation is 24. We want to be accurate within 5, and we square that value. If I plug that into my calculator, I get 62.7624, and we always round that up to the next whole number, so our minimum sample size needed here is 63. So that covers our information. Again, I'm going to highlight the fact that all of these problems gave us the population standard deviation, as that is an important part of why or how we come up with our z-scores from Table E.